Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. Lecture 17, Exponents and Roots, Part 2. We'll also be talking about order of operations at the end of the lecture. But first, let's review what we learned last time. We learned things like 5 squared. This means 5 times 5, which of course is 25. We also learned about roots. For example, the square root of 25. Well, this just undoes the squaring operation, right? So if I have 5 squared under here, the square root of 5 squared is just 5. And everyone's good with that, yes? Yes. Good. So today, we're going to learn a little bit more about roots and exponents. So the first thing we're going to learn about is called the product rule. So what does that entail? So product rule. So we're looking for the case where if we have a number, a base rather, remember that the thing that we're ready to put the exponent on is called a base. So a to the n times a to the m. Notice it's important that the base be the same when we do this. Okay, so let's discover what this rule would be. So let's try something out. Let's try 2 squared times 2 cubed. Well, we can just write this out directly, right? We can write 2 squared as 2 times 2. Put some parentheses around that. Times, now let's do 2 cubed. Well, that would be 2 times 2 times 2. Well, there's a property with numbers that is called the associative property, which means that we can put the parentheses around any groupings of these that we want. So what I'd like to do is remove this parenthesis here and here, and just consider this as one big group. Well, what's another way to write this? Well, we have 1, 2, 3, 4, 5 2's multiplied times each other. And so by the definition of the exponent that we had last time, this is just equal to 2 to the 5th. It seems that the rule, the product rule rather, for a to the n times a to the m is simply a to the n plus m. We simply add the exponents if the bases are the same. There's also a quotient rule. So in this case, we want to know what do we do if we have a to the n divided by a to the m. Well, just like before, we're going to try and figure it out by using a simple example. Let's consider 2 squared divided by 2 cubed. Like before, we'll just write this out. So 2 squared, well, that's just 2 times 2 divided by, and 2 cubed is 2 times 2 times 2. So remember the key fraction rule. If we have something in the numerator and the same thing in the denominator, we can cancel them out. That's because 2 divided by 2 is just 1. So this 2 will cancel with this 2. This 2 will cancel with this 2. And we're left with just 1 2 in the denominator. Because we want to kind of preserve our product rule form, we're going to rewrite 1 over 2 as 2 to the minus 1. So we're going to have to interpret negative exponents, meaning to take the reciprocal of that. So 2 to the minus 1 means 1 over 2. And if we do that, then we can simply say that the quotient rule is a to the n minus m. So let's apply it to the problem that we just did to see that it works. N would be 2, so 2 to the 2 minus, and m would be 3. What is 2 minus 3?
1.
Minus 1. 2 minus 3 is minus 1. So 2 to the minus 1. And so by our definition, we're defining 2 to the minus 1 to be equal to 1 over 2. And we see that our system does seem to work. So that's a little funny, granted. that we have to interpret these negative exponents, meaning 1 over that number. But once you get used to it, it'll be simple. So let me give you an example to try. Compute 5 squared times 5 cubed divided by 5 to the 4th. So go ahead and pause the video. Try that at home. Come back when you have your answer. All right, so how do I handle this beast? Well, first thing I want to do is I want to group these two right here. So we're going to work on that part first, and then we're going to rewrite the divide by 5 to the 4th with a division bar. So 5 squared times 5 cubed, we're going to use the product rule. That's going to be 5 to the 2 plus 3 power. So that will give me 5 to the 2 plus 3 power, and then I'll put a division bar in here, and I'll write this as 5 to the 4th. Let's go ahead and add those two numbers together. That gives me 5 to the 5th power divided by 5 to the 4th power. Well, now I'm set up nicely that I can apply my quotient rule. N would be 5 and M would be 4. So I can rewrite this as 5 to the 5 minus 4. And what is 5 minus 4?
Negative 1. 1.
It's 1. 5 to the 1, but we don't need to write 5 to the 1 because 5 to the 1 is just 5, right? I think we discussed that last time. And that gives us our answer. And you can see that this is right, so we could, expand this a little bit and write this as 5 times 5 times 5 times 5 times 5 divided by 5 times 5 times 5 times 5. Cancel each of these in pairs. 5 cancels this 5 cancels this 5, this 5 cancels this 5, this 5 cancels this 5, and I'm left with just a single 5 in the numerator. That's why our rules are helpful. It avoids all this extra work, and so that's why we have these rules. I'm going to call this other. It's just some extra things that we need to keep in mind. The first thing we need to keep in mind is that a raised to the 0 power is just 1. As long as a is not 0, not equal to 0. Okay, that's important to remember. Now, why would that be necessary? Well, we know that 2 divided by 2 is just 1.
Yeah.
And I could rewrite this as 2 to the 1 over 2 to the 1. Using the quotient rule, I would get that this is equal to 2 to the 1 minus 1. 1 minus 1 is 0. 2 to the 0. But I know that 2 divided by 2 is equal to 1, and so therefore I define any positive number raised to the 0 power as equal to 1. So if I were to place this with 3 to the 1 over 3 to the 1, that would also be equal to 1. So that's the reason for this little definition here. Let's see, 0 to the k power is equal to 0, where k is not equal to minus 1. And also, or 0. Yeah, that's important. 0 raised to the 0 power we do not define. We call that undefined. Because if we did define it, then it's going to clash with this rule that any number raised to the 0 power equals 1, you see? Because a is not allowed to be equal to 0. So for that reason, we say that 0 raised to the 0 power is not defined. Let me write that down. 0 raised to the 0 power is not defined. Now what about this 0 raised to the k power equals 0, except if k is equal to minus 1, in which case it's not. Why not? Well, what would that look like? Well, if we took 0 to the minus 1 power, remember that we said that negative exponents mean just take the reciprocal of that. So this would be equal to 1 divided by 0. And by definition, we don't define 1 divided by 0. That's also undefined. You've probably heard that before. You can never divide by 0. And the reason why is because if you had to give an answer, it wouldn't be a number. It would be infinity, and infinity is not a number. Does that make sense? So you can think of, like, what is 1 divided by 0.1? Well, that's 10. 1 divided by 0.01, that would be 100. 1 divided by 0.001, that'd be 1,000. And then if you just keep adding zeros in the denominator such that you get closer and closer to 0 itself, then the number gets bigger and bigger and bigger forever. Yeah, I think that's all of my special cases. One other thing we can do with this is a power rule. We'll call it a power rule. And so what we want to know is what happens if I take a number a that has an exponent, say n, and I raise that to the m power. So let's see. Let's do something. Let's look at a simple case again. Let's do 2 squared, but let's raise that to the 3 power. So 2 squared cubed. So we know how to do this. We'll start with the cube part. Cube means whatever you're cubing, multiply it times itself 3 times. So that means we'll do 2 squared times 2 squared times 2 squared. That's the cube part. Now let's unpack this 2 squared business. 2 squared is just 2 times 2. So for each of these, we'll write 2 times 2 times 2 times 2. I can put parentheses around it so you can see what we're doing here. Times 2 times 2. 2 times 2, 2 times 2, 2 times 2. Got it all in there, right? Now let's use that associative property again. And instead of associating each of these 2 by 2s like this, let's get rid of that parenthesis and that parenthesis and that parenthesis and this parenthesis here as well. And now we have one parenthesis with 2 times 2 times 2 times 2 times 2 times 2. How many 2's is that? Count them. 1,
2, 3, 4, 5, 6.
6. We have 6 2's. So we can write this in exponential form like this, 2 to the 6th. So we had a 2 and a 3 and we got 6. Obviously we can't add those two numbers because 2 plus 3 is 5. What about 2 times 3? That's 6. And that's the correct answer. So the power rule says that a to the n raised to the m power is just a to the n times m. So let me give you a problem to try. Compute 2 cubed raised to the 2 power. So go ahead and pause the video. Try that at home. Come back when you have your answer. So the power rule says that this is just going to be equal to 2 to the 3 times 2 power. Well, 3 times 2 is
6.
6. So this is 2 to the 6th. And if you want to multiply that, you can. Right? You know how to double things quickly. You could hold up 6 fingers and you could go, well, you got 2, 4, 8, 16, 32, 64. So 2 to the 6th should be 64. The next rule I'm going to call power of a product. And so what we're looking for here is to be able to answer the question, what if I have a times b raised to the n power? How do I deal with that? Let's try a simple example, see if we can figure that out. Let's do 2 times 3 raised to the, I don't know, let's just square it, huh? The 2 power. Well, we know how to do squares. That's going to be 2 times 3 times 2 times 3. Now we're going to take advantage of a couple of, we're going to again take advantage of the associativity, but also another property called commutativity. That means that the 2 and the 3 can move around. And so what I want to do is I want to move the 2's together and then move the 3's together, and then I'll use associativity again to reassociate them. So let's see what that looks like. So I'm going to write this as 2 times 2, see I move this 2 over here, times 3 times 3. I'll put parentheses around these like this. Associative property again. And now I know how to write 2 times 2. That's just 2 squared. And I know how to write 3 times 3. That's just 3 squared. And so you can see what the rule is. A times b to the n power is just a to the n times b to the n. Now sometimes I use a dot for multiplication. Sometimes I use the multiplication sign. I'll just fix that there. If you see that, don't get confused. The dots also mean to multiply. All right, so let's try an example of that one. So compute 2 times 3 cubed. So let's do 2 times 3 raised to the 3 power. So pause the video, try that at home, come back when you have your answer. Now, I'm just going to use the rule, and the rule tells me that this is equal to 2 cubed times 3 cubed. And who remembers what 2 cubed is? 2 cubed is
8.
2 cubed is 8 times, and what is 3 cubed?
27.
27. 8 times 27. Now you can do that long multiplication. You can try that at home if you want to. We're not going to do it here. We're going to move on. Related to the power of a product is we also have a power of a quotient. And I'm not going to justify this, but it's exactly what you'd expect it to be. If we have a divided by b raised to the n power, that's going to be a to the n over b to the n. But make sure when you get this, always reduce first. So this is a to the n over b to the n. It's not going to change anything, but it will make the number smaller and easier to work with. So for example, if I had 2 over 4 raised to the 3 power, instead of dividing 2 cubed by 4 cubed, I could have just divided 1 cubed divided by 2 cubed, which is much easier, you see. One important thing to note here, I should write that in now, that b cannot be equal to 0. Why? Because we cannot divide by 0. Therefore, b can't be 0. All right, let's look at roots. How do you think we write roots as an exponent? Any ideas? So what do I mean by roots? Remember, this is a root. You could even write this for the nth root of some number a. So let's take an example. Let's see. 2 squared, we know, is equal to 2. Because the square root is the inverse of raising something to the 2 power. So if I square something and then I immediately take the square root of it, I get that something back. The question is, the nth root, we'll say, of a is equal to a to the question mark power. How can we write something like that? Well, working with our square root of 2 equals 2 example, write 2 squared, and I raise that to some, I don't know what, so I'm putting a question mark for the exponent there. It's going to be equal to 2 to the 1, you see? So that means that 2 times this question mark must be equal to 1. Now what can I multiply 2 by to get 1? 2 times something will equal 1. Could be 1. What's 2 times 1?
2.
Okay, that's too big. So something smaller than 1 then, huh?
0?
Well, 2 times 0 is 0. That's not going to work.
-1?
2 times -1? Well, that would be -2. I need it to be equal to 1. No, there is something. If I were to multiply 2 times a half, then I will get 1, right? Because the 2 will cancel, the 2 in the numerator will cancel the 2 in the denominator, and I'll get 1, yes? So roots, the nth root, is actually a to the 1 over n power. So that's how we write roots as an exponent. So let me just copy this here. Equals a to the 1 over n power. What about this? What if I wrote, let's try this at home and see if we can figure this one out. What about the nth root of a to the mth power? How do we write that? So let's pause the video, take a crack at it, come back when you think you have an answer. Well, a to the mth, we already have that. So we can kind of think of this as this thing that we want to raise to the 1 over n power. So we'll write this as a to the m raised to the 1 over n power. We'll then use the power rule to rewrite this as a to the m times 1 over n. But that is the same thing as a to the m over n power. Does that make sense? Good. Okay, you're going to get plenty of practice in the homework with roots and exponents and stuff. I put a good number of problems in there. You'll have fun with that. The last thing I want to talk about is what's called order of operations. So let's start with an expression, 3 plus 4 times 5 squared minus 6 divided by 2 minus 1. A lot of operations put together there, huh? Now, traditionally, the way that this is taught is called PEMDAS. It's an acronym. It stands for parentheses, which we have none of here, exponents, multiplication, division, addition, subtraction. That's what they call the order of operations. And with the additional rule that we always work from left to right. So you work from left to right, you do the parentheses first, then you take care of the exponents. We have an exponent here, so we'd write 5 squared is 25. Then you do the multiplications. Well, we do 4 times 25, and there are no other multiplications to do. Then we do the divisions, which left to right would be minus 6 divided by 2. And then we do the additions, 3 plus this product, no more additions. And then we do the subtractions, this minus this term and then minus 1. Okay? But I really, really hate order of operations and PEMDAS. So instead, I have a slightly different way of looking at things. The first thing is grouping. And I suppose if I wanted to, I could put some parentheses in here, so we at least have an example with parentheses. That would mean do everything in the parentheses first. So the types of grouping that you're looking for parentheses. That's not the only way to group things. Sometimes you'll see brackets like this. And sometimes you'll see curly brackets. Other groupings that you can see are roots. If you see something under a root sign, that's a bracket. A division bar, like A divided by B. That's a grouping. So grouping first. So do the things that need to be grouped. So I'll give you an example. Let's consider 3 times the square root of 3 times 3. Well, we do everything. The grouping here is the root symbol. So we do the root first. We'll do 3 times, well, what is 3 times 3? That's 9, which is just also, you can think of it as 3 squared. That's probably the easiest way to deal with it. And so now we evaluate the root, and that's 3 times 3, because the square root of 9 is 3. So we do the root first. Then we can do whatever's left behind, which is just 3 times 3. Exponents bind to their immediate base and are right associative. So what do I mean by that? Well, if we had AB squared, this is equal to A times B squared. It is not equal to A times B squared. Similarly, A raised to the B power raised to the C power, this is equal to A raised to the B raised to the C power. So if I did an example, let's say this was 2 raised to the 2 raised to the 3 power, this would be equal to 2, what is 2 cubed?
4.
So yeah, first I do this. Whoops, I kind of erased my 2 cubed. So I first do this. 2 cubed is 8. And so that's what I'm left with. 2 to the 8th power. That's the right associativity part. These are bullet points here. So next. A minus B is equal to A plus negative B. And A divided by B is equal to A times 1 over B. So what does that mean? That basically means there's no such thing as division, and there's no such thing as subtraction. We convert all numbers to sign numbers, and we turn all divisions into multiplications. So we'll only have multiplication and addition to worry about. And finally, multiplication and addition are associative and commutative. So that basically gets rid of the left to right working order. You can work it in any order that you want, provided that you do these things. You observe the grouping property, you bind the exponents to their immediate base and do so in a right associative manner, that you make all numbers signed numbers and you turn all divisions into multiplications. Then whether you work from left to right, right to left, middle out, doesn't matter. Probably seems pretty confusing, so let's look at some examples. For starters, how do we do this up here? Let me just... Yuck. So how do we work this one up here? Well, the parentheses come first. So we've got 3 plus 4 times 5 squared. Well, that's going to be 3 plus 4 times 5 squared. What is 5 squared?
25.
It's 25. And what is 25 times 4? That's the way I want you to look at it. 4 times 5 times 5. So you can do it in any order you want. If you want to do 4 times 5 is 20 times 5 is 100, or you want to do it 5 times 5 is 25 times 4 is 100, doesn't matter. This is 100. This is 3 plus 100. So this whole thing goes to 103. Minus 6 divided by 2 minus 1. We'll get rid of that minus divided by 2. We're going to rewrite that as times 1 over 2, which is the same thing as doing this. We're going to get rid of this minus signs. We're going to make this plus minus 1. We're going to make this plus minus 6 over 2. That's a grouping. Let's go ahead and do that. 6 over 2, that's 3. So now I have 103 plus negative 3. What's that?
100.
100. Plus negative 1. What is 100 plus negative 1? 99. So we get our answer 99. Let's look at a couple more examples. With addition, things can really work out nicely for you with grouping. Let's see. Where's my example? Let's look at 7 plus 6 plus 3 plus 4 plus 8. So when you get something like this, what I want you to do is associate terms that are nice. So the 7 and the 3, what happens when I add 7 plus 3?
10.
It's 10, right? What happens when I add 6 and 4?
10.
It's also 10. And then I finally have an 8 left over here at the end. So I can see quickly, just by looking at this, the 7 and the 3 gives me 10, the 6 and the 4 gives me another 10. I'm up to 20, and then I got 8 to add on, so this must be equal to 28. As opposed to the classic left to right order, 7 plus 6, what is that? 13. 13 plus 3 is
16.
16. 16 plus 4 is
20.
20, and 20 plus 8 is
28.
28. So I think it's much easier whenever you group things in groups of 10s. 7 plus 3 is 10, 6 plus 4 is 10, that's 2 10s, is 20 plus the 8, and I'm done. You see? Makes it much easier. Let's look at, as just a final problem, let's consider without the parentheses, 3 plus 4 times 5 squared minus 6 divided by 2. So go ahead and try that one at home. Come back when you have your answer. Well, we got to get rid of these subtractions and turn that into plus a negative 6. Get rid of that division, turn that into a divided by 2, or 6 times 1 over 2. We can put parentheses around this to remind us that we're only associating that square, that 2 exponent, with the 5. And then we can do it in any order we want. So maybe we like to do this and this first, because what is minus 6 over 2? That's a grouping. Let's go ahead and do that. What is 6 over 2? 3. So that becomes a minus 3. So obviously that's what I want to do. I want to take the 3 and combine it with the negative 3, because that is 0. Good. So all I'm left with is 4 times 5 squared. Again, I can do it in any order that I want. This is just 5 times 5. 4 times 5 is 20, times 5 is 100. Or, if I prefer, 4 times 25 is also 100. And so I get 100 for my final answer. That's all I got for you today. Honestly, I forgot what we're doing in the next lecture. Maybe I'll put it up at the end there. Do you know what I'm doing in the next lecture? Quantum field theory? Is that what comes next?
I don't think it's that.
Don't think so?
Coordinating graphing.
Coordinate graph. Oh, so graphing's in the next lecture. Okay, interesting. So we'll be doing graphing in the next lecture, apparently. No promises on that. All right, well, I'll see you then.